Hello friends, continuing with the chapter of communication systems. Today we come to its fourth part, that is communication systems part 4. In this part we will study about modulation. What is modulation? Let us define. The process by virtue of which modulating signal is superimposed over carrier wave and either amplitude, frequency or phase of the carrier is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two constant, is defined as modulation. I repeat, the process by virtue of which modulating signal is superimposed over carrier wave and either amplitude, frequency or phase of the carrier is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two constant. This is modulating wave. This is carrier wave. Now here modulating wave is superimposed over carrier wave. Now when the two waves are superimposed, they interact with each other. So one of the three parameters, amplitude, frequency or phase, is varied according to instantaneous amplitude of the modulating signal. Okay, so this process we call it as modulation. So here we have superimposition of waves, that is carrier wave and modulating wave. Now second step, need of modulation. Why we require modulation? Let us try to understand. First, in order to have a convenient length of radiating element, we need modulation. Second, to have effective power radiated by radiating element, we need modulation. Third, to avoid mixing up of signals transmitted by various transmitters, we need modulation. We take up one by one. First, we take up to have convenient length of radiating element. How we can have convenient length of radiating element? Let us try to understand. The base band frequency range is 300 Hz to 20 kHz and is the audio frequency range to which human ear can give response, and sometimes called as information band. If we transmit this band directly in the form of electromagnetic waves, then minimum length required for transmitting 20 kHz frequency would be given by the expression lambda equal to c by nu, or lambda is equal to 3 into 10 raised to power 8 meter per second for c, velocity of light, and 20 into 10 raised to power 3 hertz, frequency nu, and it comes out to be 15 into 10 raised to power 3 meter, or it is equal to 15 kilometer. The length of radiating element required will be 15 kilometer, which is not very convenient. If we mount 20 kilohertz over a high frequency carrier, say 1 megahertz, then length of radiating element would be lambda equal to 3 into 10 raised to power 8 meter per second divided by 1 into 10 raised to power 6 hertz, and it is equal to 300 meters, which is very convenient as compared to 15 kilometer. Hence, need of modulation arises. Now second, to have effective power radiated by radiating element. Now, effective power radiated by radiating element is given by the expression L by lambda whole square, where L is the length of radiating element, or we can say the effective power radiated by radiating element is given by the expression L into nu by C whole square. Since C is equal to nu lambda and 1 by lambda would be equal to nu by C. Since effective power radiated by radiating element is directly proportional to square of the frequency, therefore radiating at high frequency is more effective, hence need of modulation arise. Now, from this expression you can see that effective power radiated is directly proportional to square of frequency. Okay, therefore we say radiating at high frequency is more effective, hence need of modulation arise. 3. To avoid mixing up of signals transmitted by various transmitters. The audio information band ranges from 300 Hz to 20 kHz. If every transmitter will transmit signals in the same band, the signals would get mixed up and nothing could be followed. Like if in a class all students will start speaking, then the teacher cannot make out anything. Similarly, if every transmitter will transmit signals in the same band, the signals would get mixed up and nothing could be followed. It is therefore high frequency bands like 500 kHz to 1500 kHz, 3 MHz to 30 MHz and 30 MHz to 300 GHz bands are selected, and a particular frequency is allotted for transmission to every station to avoid mixing up of signals. Hence, need of modulation arise. Now, third point we have to understand is modulation and systems of communication. You know, we have two systems of communication: analog communication system and digital communication system. Analog communication systems use amplitude modulation, frequency modulation and phase modulation, that is AM, FM, PM respectively. And digital communication system involves pulse modulation, that is pulse amplitude modulation PAM, pulse width modulation, that is PWM, or sometimes we call it as pulse duration modulation PDM. And third one is pulse position modulation, that is PPM, and fourth one is pulse code modulation PCM. So this way we have different types of modulation with different systems. Accordingly we'll take up one by one. Now, fourth point in this topic is types of modulation in analog communication systems. As I already told you that there are three types of modulation in analog communication system. That is, first is amplitude modulation, second is frequency modulation, third is phase modulation. Let us take up one by one. First we take up amplitude modulation. Now let us define amplitude modulation. A. Definition: the process by virtue of which modulating signal, this modulating signal is superimposed over carrier wave, this carrier wave, and amplitude of the carrier is varied in accordance with the instantaneous amplitude of the modulating signal, keeping frequency and phase of the carrier constant. I repeat, the process by virtue of which modulating signal is superimposed over carrier wave here, and amplitude of the carrier is varied in accordance with the instantaneous amplitude of the modulating signal, keeping frequency and phase of the carrier constant. So this is the final modulated wave. Now look at this diagram. This is modulating wave, this is carrier wave, and here we have the superimposition of waves. Carrier is mounted with audio, and as a result of superimposition we have this modulated wave in which amplitude of the carrier is varied in accordance with the modulating signal. Okay, so this is amplitude modulated wave. B. Mathematical expression of modulated wave. Let EMT is equal to EM max sine omega t be the modulating signal. Mark it as equation 1. This is the modulating signal or modulating wave superimposed over carrier wave ECT equal to EC max sine omega CT. Mark it as equation 2. So this is carrier wave. Now this modulating signal is superimposed over carrier wave here in the third phase. This is carrier wave and this is modulating wave. So modulating wave is superimposed over carrier wave. Now then the amplitude of modulated wave at any instant of time according to definition can be expressed as E mod t, mod for modulated, E for amplitude at any instant of time t, that is equal to ECT plus Ka times EMT, where Ka is constant of proportionality for amplitude modulation, A for amplitude, Ka for constant. Ka is constant of amplitude modulation. Substituting the value of ECT from equation 2 and EMT from equation 1, we get E mod equal to EC max plus Ka EM max sine omega mt into sine omega Ct, because it is the amplitude of carrier wave which is changed according to the instantaneous value of modulating signal. So therefore we write E mod equal to EC max plus Ka EM max sine omega mt into sine omega Ct, or E mod is equal to EC max sine omega Ct plus Ka EM max sine omega mt sine omega Ct. After opening the bracket we can write it like this, or E mod is equal to EC max sine omega Ct plus Ka EM max divided by 2 multiplied by 2 sine omega Ct sine omega mt. Let us mark it as equation 3. So here we have multiplied the second term by 2, second term means this term, by 2 and divided by 2, this 2. Okay, so it hardly matters. So this is the modulated wave where we can estimate the variation in amplitude of the carrier according to instantaneous amplitude of modulating signal. Okay. Now further, using the formula 2 cos A cos B as cos A minus B minus cos A plus B, we can write equation 3 as E mod is equal to EC max sin omega Ct plus Ka Em max divided by 2 into cos omega C minus omega mt minus cos omega C plus omega mt as it is. Okay. Or we can write E mod is equal to EC max sin omega Ct plus Ka Em max divided by 2 into cos omega C minus omega mt minus Ka Em max divided by 2 into cos omega C plus omega mt. Let us mark it as equation 4. Equation 4 is the final expression for amplitude modulated wave. This expression reveals that amplitude modulated wave contains three components. First, the carrier itself, ECT is equal to EC max sin omega Ct, this first term. Second, the lower sideband LSB containing information and is Ka Em max divided by 2 into cos omega C minus omega mt. And third component is the upper sideband USB containing information, which is Ka Em max divided by 2 into cos omega C plus omega mt. Okay. Now this is the curve showing relationship between amplitude and frequency of the modulated wave. Here this is omega C minus omega m. This is central frequency omega C, that is carrier wave. Omega C minus omega m is the lower sideband and omega C plus omega m is the upper sideband. Okay. So thus a modulated wave contains three components: carrier itself plus lower sideband containing information as well as plus upper sideband containing information. Information is contained in both the bands, the lower sideband as well as in the upper sideband. Okay. Now see disadvantages of amplitude modulation. Number 1, out of three components, two components LSB and USB contain same information and we can recover back information from only one sideband, either LSB or USB. But we are bound to transmit all the three components. Therefore, 66.6% of the power transmitted is wasted. Only 33.3% is useful power. I repeat, number 1, out of three components, two components LSB and USB contains same information and we can recover back information from only one sideband, either LSB or USB. But we are bound to transmit all the three components. Therefore, 66.6% of the power transmitted is wasted. Only 33.3% is useful power. Now we come to second disadvantage. Amplitude modulation system is very noisy. Quality of information depends upon signal to noise ratio. Okay, these are the two main disadvantages of amplitude modulation. That is 66.6% power is wasted and quality of information depends upon signal to noise ratio, and it is very noisy. D, modulation index. Let us define. Degree of modulation is defined as modulation index. I repeat, degree of modulation is defined as modulation index. Mathematically, it is defined as the ratio of amplitude of modulating signal to the amplitude of carrier wave. I repeat, mathematically, it is defined as the ratio of amplitude of modulating signal to the amplitude of carrier wave. If MA be the modulation index, then MA can be written as equal to Ka into Em by Ec, where Ka is constant of amplitude modulation. and is expressed as Ka into Em by Ec into 100%. In terms of percentage, we represent modulation index. Alternative definition of modulation index: ratio of maximum amplitude minus minimum amplitude to the maximum amplitude plus minimum amplitude of the modulated wave is defined as modulation index. Mathematically expressed as Ma is equal to Emax minus Emin divided by Emax plus Emin, or we can write Ma is equal to Emax minus Emin divided by Emax plus Emin into 100%. Now look at this diagram. This is the carrier amplitude Ec. This is the maximum amplitude of modulated wave, and this is the minimum amplitude of modulated wave. Maximum is Emax and minimum is Emin. So we can write Ma is equal to Emax minus Emin divided by Emax plus Emin into 100%. We multiply by 100 for writing it into a percentage. Okay. So this is alternative definition of modulation index. Now assignment 15 continued. Question number 16. We do not choose to transmit an audio signal by just directly connecting it to an electromagnetic wave of the same frequency. Give reasons for the same. Question number 17. Define the term modulation index for an AM wave. What could be the modulation index for an AM wave for which maximum amplitude is A while the minimum amplitude is B? Question number 18. A message signal of frequency 10 kHz and peak voltage of 10 volts is used to modulate a carrier frequency of 1 MHz and peak of 20 volts. Determine A. Modulation index, B. the sidebands produced. So here is the answer for modulation index, and this is the answer for lower sideband as well as upper sideband. Okay. Thank you so much. Next time we'll continue with this topic and we'll take up frequency modulation. Till then, goodbye and good luck to you.